In recent decades, thousands of new planets have been discovered beyond our solar system, the so-called exoplanets, objects orbiting other stars that obviously at best have only been observed as small and simple dots. However, in the next few years, it is very likely that we will be able to observe the morphology and some characteristics of the surface, such as the presence of vegetation, mountains, or even signs of habitability. If this will happen, it will be thanks to a new project funded by NASA that plans to make a natural telescope based on the property of light to be focused by means of a large mass that acts as a gravitational lens. Okay, let's figure this out. A gravitational telescope capable of showing the morphology and surface of exoplanets. The search for an Earth-like planet orbiting another star is one of astronomy's greatest challenges. It's a task that appears close to fruition. Since astronomers spotted the first exoplanet in 1988, they have found more than 4,000 others. Most of these planets are huge because bigger objects are easier to spot. But as sensing techniques and technologies improve, astronomers are finding planets that match Earth's vital statistics even more closely. They have even begun to use a ranking system called the Earth Similarity Index to quantify how similar an exoplanet is to the mother planet. The exoplanet that currently ranks most highly is Kepler 438b, which orbits in the habitable zone of a red dwarf in the constellation of Lyra, some 470 light-years from here. Kepler 438b has an Earth Similarity Index of 0.88. By comparison, Mars has an ESI of 0.797. So it's more Earth-like than our nearest neighbor. That's exciting, but it is inevitable that astronomers will find planets with even higher indices in the near future. And that raises an interesting question. How much can we ever know about these planets given their size and distance from us? To understand the magnitude of the problem, let's imagine we want to observe the Earth from a distance of 100 light-years. From such a distance, our planet, which has a diameter of about 12,750 kilometers, subtends an arc of just 3 millionths of an arc-second, an angle 17,600 times smaller than the smallest detail that a large telescope like Hubble, for example, is able to resolve and show us. And this is without considering that from such a distance, the weak light reflected from Earth would be completely drowned in the overwhelming glare of the sun. If we wanted to be able to see the Earth as a disk and not as a simple point of light, we would need a telescope with a mere not 80 meters in diameter, already huge for our construction standards, but of 80 kilometers. If we then wanted to obtain a detailed image with a resolution capable of showing us seas and continents, we would need a telescope with an aperture of about 50,000 kilometers. That is 4 times larger than the diameter of Earth. What should we do then? Give up forever the possibility to have a look at the confirmation of an alien planet? Maybe yes, maybe no. Imagine having an instrument on an extrasolar planet that would allow you to observe not only the shapes of their continents and oceans, if they have any, but details just a few kilometers large. It would be a revolution not only technological but also cultural. It would make very clear to us the concept that the Earth is only one of an infinite number of worlds. Well, perhaps you will be surprised to know that this tool is already feasible with existing technologies or their refinements. It is called Solar Gravity Lens and works using a fascinating technique. Its primary lens, in fact, is an entire star, in this case, our Sun. It is not pure theory. Astronomers have already observed this phenomenon in concrete images of distant galaxies, whose appearance is deformed because their light comes to us passing in the vicinity of another celestial body of large mass, for example, another galaxy relatively closer. The fact that a concentrated mass is able to deviate in a measurable way the path of light is one of the cornerstones of general relativity and the principle at the base of the functioning of gravitational lenses. We must always remember that Einstein became world famous only in 1919, when the English scientist Arthur Eddington was able to demonstrate, thanks to photographs taken during a total eclipse of the sun, that the theory of relativity correctly predicted the small shift, caused by the mass of the sun, of the position of some stars randomly aligned with the solar edge. But the sun's mass can do more than slightly deflect the path of light rays passing in its vicinity. If a light source is located exactly behind the sun with respect to the position of an observer, then looking in the direction of the sun from a sufficient distance, the observer will see around the solar disk a ring-like structure that contains the image, distorted and magnified, of that source. It is the so-called Einstein ring, the most perfect example of gravitational lens. Thanks to this optical phenomenon, it is possible to observe objects that would otherwise be invisible even for the most powerful telescopes. The mass acting as a lens produces, in fact, two extraordinarily favorable effects. It magnifies the remote source randomly aligned with the observer and greatly enhances the light intensity. Okay guys, hang on a sec before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. If you'd like to help improve the quality of our content, please check us out on Patreon. We would like to say a big thank you to all those who show their support. It should be immediately clear that it is not at all easy to succeed in using a gravitational lens for such a purpose, but it is possible. And the fact that it is possible is evidenced by the only project that has reached Phase 3 of the 2020 selection of the NASA NIAC program. NIAC stands for NASA Innovative Advanced Concepts, and as the name suggests, it's an initiative that rewards innovative projects for future space missions, offering more and more funding as a selected project passes the preliminary stages, in which its feasibility and the degree of completeness of the idea is evaluated. The project now in Phase 3 of this year's edition is called Direct Multi-Pixel Imaging and Spectroscopy of an Exoplanet with a Solar Gravitational Lens Mission. Its promoters are Slava Turyshev, a Russian physicist working at NASA Jet Propulsion Laboratory, and Viktor Toth, a software developer who has advanced knowledge of physics and is the author, often together with Turyshev, of numerous studies published on some of the major scientific journals. The object that ends up under the gravitational lens is magnified to the point that a telescope with a 1-meter primary mirror could reach, observing the image produced by the lens, an angular resolution of 1/billionth of an arc second. With such a resolution, details on the order of kilometers could be resolved on the surface of an exoplanet up to 100 light-years from Earth. It would be possible, for example, to see the lights in the night hemisphere of the planet, if it was inhabited by a technological civilization capable of illuminating the night, covering vast territories with artificial lights as we humans do. Why this extraordinary possibility of knowledge has not been exploited before? For at least two good reasons. The first is the difficulty to reconstruct the image of the exoplanets from the Einstein ring, from which begins to be visible the Einstein ring that contains the image of the exoplanet. Let's start from the first point. Gravitational lenses are not perfect lenses. The images they produce, although exceptional from the point of view of magnification and enhancement of light intensity of the source, are severely distorted due to an optical phenomenon called spherical aberration. As a result of it, the light rays from the remote source are bent at a variable angle, which depends on the distance at which each ray passes relative to the mass acting as a lens. Because of spherical aberration, there is not a single focal point where all the light rays converge, but a focal line, which continues indefinitely as one moves away from the mass acting as a lens. Because of spherical aberration, each point of the Einstein ring formed by light from an exoplanet aligned with the sun, and the observer contains a superposition of images. A complex mathematical analysis of how light rays from different parts of the planetary surface interact with each other is therefore required to hope to faithfully reconstruct a sharp image of the exoplanet observed through the gravitational solar lens. To make things more complicated, there is a secondary problem, in that the source focused by the gravitational lens continuously changes its appearance. An exoplanet observed through an Einstein ring is in fact not an immobile object. It orbits around its star and rotates around its own axis. This means that the portion of the planetary surface observed at any point along the focal line created by the gravitational lens changes very rapidly. The rapid variability is a consequence of the fact that the very high resolution of the gravitational lens allows to observe extremely small regions of the light source, a few tens of kilometers long at most. It is like having a very small window inside which portions of the surface of an object flowing continuously. Taking into account all these factors and others, the reconstruction of a detailed image of an exoplanet observed through the solar gravitational lens will inevitably be a long and extremely laborious operation. First of all, the space telescopes, if there will be more than one, sent in the area where the Einstein ring will be visible, will have to find the exact place where the image of the exoplanet is formed. The second major obstacle to the use of the solar gravitational lens is the distance to which one must travel to reach the focal point of the whole system. Given the mass and radius of the Sun, the minimum distance at which the ring becomes visible is about 550 astronomical units. The astronomical unit is the average distance between the Earth and the Sun, and corresponds to just under 150 million kilometers, equal to 82 billion kilometers. It is an immense distance to which no probe built by mankind has so far never reached. The Voyager 1 launched in 1977 is the most distant human artifact to date. After 44 years of travel, it arrived at 23 billion kilometers from the Sun, only a quarter of the distance that must be covered to arrive in the area useful to exploit the solar gravitational lens. It is understood from this data that the probe or the group of robotic probes that will have the task of observing the solar gravitational lens will have to possess a much higher speed, more than 5 times greater than that with which Voyager 1 is moving away from the Sun. But it is probably not a good idea to invest years of planning on a single heavy and expensive probe. A wiser option would be to launch a whole fleet of very light and inexpensive robotic probes propelled by solar sails. What would be lost in quantity and power of the scientific instrumentation at single craft level could be regained with interest through the redundancy of observations guaranteed by the availability of a large number of space telescopes, all engaged in the same task, coordinated by an artificial intelligence that learns by trial and error. Among other things, a spacecraft equipped with solar sails would continue to accelerate all the time instead of having only the brief initial queue of traditional rockets. The result is that a solar sail carrying a telescope could reach the Sun's focal point in about 25 years. Arriving at the right distance and in the right position, the telescope would point its sensors in the direction of the Sun, equipped with a coronagraph capable of blocking light from the solar disk. This would allow the telescope to capture the image of an exoplanet distorted in an Einstein ring, placing itself so as to have the Sun exactly aligned with that exoplanet. In reality, the ring would be double. One would contain light from a single area about 10 kilometers in diameter of the exoplanet, while the other would contain light from the rest of the alien world. Slightly moving the telescope about a kilometer in different directions would change the area of the exoplanet framed by the first ring, and then you could do a slow scan of its entire surface. Observing these distortions for 6 months and processing about 1 million images collected, it would be possible to exclude the light of the solar corona and obtain an image similar to that simulated shown at the beginning of this article, even eliminating any clouds. In addition to the image of the surface, this telescope would also do spectroscopy of the exoplanet, allowing to know the chemical composition of its eventual atmosphere. If an alien civilization were to do this with us, pointing a solar gravitational lensing telescope at Earth, it could detect the sudden increase in atmospheric CO2 and other pollutants and infer the presence of industrial activities by the planet's unwise inhabitants. Building a gravitational telescope is, in short, a remarkable engineering challenge, involving exceptional navigational precision and unprecedented radio communication difficulties, but requiring nothing we do not already know. A fleet of these telescopes placed in various points of the circumference surrounding the Sun at a distance of 550 astronomical units could observe in a few decades all the planets located less than 100 light-years from Earth. If all this seems too sci-fi, and if the idea of being able to see the continents of distant worlds seems unfeasible, consider what I said before, and that is that NASA is so interested in this concept to fund research on its feasibility with $2 million. And if they believe in it, why shouldn't we believe in it?